ask me about like, you know, how did I decide to be an astrobiologist? You know, I tell them like I really loved it and I went into it full bore because of that. And it's important like to find something you love to do for your life. And I think we've heard that kind of advice. The second thing I like to tell kids is find something you can do where you'll love the people you work with. And you know, Kennda mentioned we're colleagues and friends, and it means so much to me to have people across the country and across the world that I've been working with that I really respect and admire as people and as friends as well as colleagues. So thank you, Kennda, for that introduction. Thank you, Ironmonger, for having us here, and thank you, Atlanta Science Tavern, for letting me speak a little bit tonight. I am Shawn Domagal-Goldman. If you want to hit me up on Twitter, I'm at Shawn D Goldman. And I'll be talking about the search for life tonight. And I'll be talking about this from the context of all of the places that NASA is planning to search for signs of aliens, you know, life beyond Earth, over the span of our lifetimes, right, over the next 20 to 30 years. And I'll be doing that from like the standpoint of Mars, Europa, Titan, exoplanets. And the thing I just want to point out is like I'm one person standing up on this stage, but you almost have to imagine like an army of people behind me, because the thoughts I'm putting out are coming from the Virtual Planet Lab, which is located in Seattle, Washington. This is the big science team that I'm helping lead out of NASA Goddard, the HabEx and LUVOIR teams, which are telescopes I might talk about later. Nexus, which is an international science collaboration, Mars Science Lab, which is more popularly known as Curiosity, that's the rover on Mars right now, and of course the agency. Because you know, this is one of those things where the problems are actually really hard to do. Like I really believe the smartest person in the world, I don't think if Albert Einstein were alive, he could do this science all by himself. I think it actually takes a community of people where there's expertise spread out across different disciplines. Before I even get into that, because a lot of times I think there's some confusion about what we're talking about when we say aliens, right? So I like to start with like this little story, right? I used to walk into a bar and someone would ask me if I was just sitting at a bar stool, like, what do you do for a living? And I used to say, like, I look for aliens, right? So I would do that. But inevitably, what would happen is they'd get this picture in their mind. Keep going, Mike. Yeah, or that person, or that thing. Or, you know, if you're from my generation, this is what you had in your mind, Kodos or Kang. Or E.T. if you're from my generation as well, right? And actually, which alien you're thinking of is probably like dating you a little bit. So now I say I look for ways to look for life on other planets. Next slide. And then people start to get something like this in their head, which is much closer to the truth, right? Because I work for the most part on spacecraft. And at NASA, what we do is we turn the question of, are we alone, into something that, like, we take it out of the bar room, right? And that's fun. Like, I actually like speculating, and like, there's a lot of good science that starts in a bar room where we're just like kicking ideas around over a beer, or a glass of wine, or a soda. But taking it from that space into a place where we can apply the scientific method, where I can make a prediction of something that's happening beyond Earth, that we could then build the spacecraft to make a measurement to test that prediction. And because that's how science works, right? We make a prediction, we test it with observation, and if our predictions are wrong, we refine our models and our theories to make a new prediction for somewhere else. So this takes me back like about 20 years, and this goes back to this story of like how I decided to be an astrobiologist in the first place. I grew up in Chicago, and so like here, you know, you can't necessarily do much astronomy, right? Like there's too much light pollution. And one night, so we usually couldn't see the stars, we definitely couldn't see the Milky Way like you can see in this beautiful image. But one night there was a lunar eclipse, and I remember standing on the front yard with my little brother. I was in college at the time, and I was, you know, figuring out what I wanted to do with the rest of my life. I call that like the quarter-life crisis, when you're figuring out like, what am I going to do with the rest of my life? So I was sitting there on the front yard during a lunar eclipse, so we could actually see the stars for a change. My brother turned to me and he said, "You think there's anybody out there?" And it hit me, because I was like, man, I don't know, but that sounds like a pretty cool problem to address or to tackle. And so I started looking into like places I could do that for research or for grad school, and that led me down a path to being an astrobiologist. All right, so I'm not the first astrobiologist. I'm hopefully not the last astrobiologist. We've actually been doing at NASA a search for life around on planets beyond Earth for a long time. Actually, the first explicit experiment in this space was done by the Viking rover decades ago, right? The Viking lander, I should say, decades ago, right? So this is a paper, if you can't see it from the back, from 1976. And this is from a specific measurement called the radio, and there's no data on here yet. I'll show it in a second. This is how we turn a theory that there's life on Mars into a testable observation. The theory was like, if there's life on Mars, maybe it's starved for food. So what we're going to do is we're going to pick up some Martian soil, we're going to put it into the lander, And then once it's in the lander, we're going to heat it up a little bit, and we're going to give it some food. We're going to give it some nutrients and stuff like that. And we made those nutrients radioactively labeled. And the reason we did that is it would become very easy to detect the gases that the life would give off if they were radioactive, because you can see radioactive stuff really easily with an instrument. And this, what I'm going to show you in a second is data from the instrument where if there's radioactivity, you'll see it go up over time when we introduce the food with the radioactively labeled food in there, right? All right, so next slide, let's see what the data look like. The prediction, it was exactly what happened. You put the food in right here, and all of a sudden we saw this spike in radioactivity from presumably the microbes living in the soil, munching on that food, turning it into gas, just like we're turning food into gas in our stomachs right now and releasing it as carbon dioxide. They saw that spike in radioactivity. And the person that led this experiment, Gil Levin and his colleague Patricia Stratt, to this day, they will not just tell you, they would get in a shouting match with me to say that they're the first group to find evidence of life beyond Earth. Now, for me, coming into astrobiology now, this is actually a cautionary tale because the majority of the astrobiology community does not accept this as definitive proof of life. And the reason is, it's not that this experiment in and of itself was a failure, it's that the story is much more complicated than that. There were 3 other experiments on board that same lander at the same time, and even though this had a positive result, the others all had negative results. And there was a 4th experiment that was looking for carbon, organic carbon in the Martian soil, and it found there was no organic carbon in that soil to begin with, which is the stuff that we're all made of. So if you don't have the stuff life is made of, it was really hard to argue that there was life there. And now I know some people are probably thinking, well, what about the weird stuff that's not made of organic carbon? We'll get into that later. But the main message here is like, and actually go to the next slide, because I've got a few examples of this. So we've declared that we've found life before, and we've been wrong. Or at least the astrobiology community hasn't been convinced yet, is probably a safer way to say it. So this is a picture of some scientists down in Antarctica. What they're doing is they're hunting for meteorites. The reason they do this in Antarctica is meteorites are dark rocks, and Antarctica is like super bright because it's covered in ice and snow, and so the rocks stand out really, really easily, and they can find them. So next slide, Mike. So they're finding these rocks. Also, this is about 20 years ago, in 1997, 1996, 1997. David McKay and colleagues came out with this. Does anyone remember this picture from about 20 years ago? So this is the Allen Hills meteorite. This is one of those meteorites they found in Antarctica. They brought it back to the labs here in the United States, and they analyzed them, and they found multiple lines of evidence that there was ancient life in this rock, and that life was so ancient it actually took place when that rock was still on Mars, because this particular meteorite originated on Mars. And they published a paper saying that we have evidence that life was there, this rock was on the surface, it got ejected by a meteorite, hurtled across space, and then landed in Antarctica, where we found it, brought it to our labs, and found this evidence of life. Next slide. And it included these structures here. And then what that kicked off was a lot of thinking about could we make those structures, those things that look a lot like life, right? And back before the McKay et al. Work, where they claimed the Allen Hills meteorite had life, the story of whether or not something was alive, like our proof as scientists, was something like the Supreme Court's definition of pornography, which is we'll know it when we see it, right? But it turns out, because that looked like life, that last slide. This looks like life, and this looks like life, right? If I saw this, I'd be like, yeah, I know what that is. Not pornography. I'd say that's cells, right? They are naked, though, so, who knows? But actually, these aren't cells. These are mineralogical features that were made explicitly to try to recreate some of the structures that look extremely creepy, crawly, and lifelike. Next slide. All right, and if you think I'm picking on the Martians, because those were both Martian stories, this actually also happens on Earth, right? If you look in the literature for the oldest evidence of life on Earth, there's these microfossils, or what were argued to be microfossils, from over 3 billion years ago. And this, if you ever have a scientist that's learning about scientific debate, have them research the earliest evidence for life on Earth, because it's super contentious. Next slide. And I'm highlighting this here mostly to get at one word. If you can't read it in the back, it's this one, dubiofossils, right? This was a response to those fossils I was showing. Another scientist, this is the equivalent of scientists swearing at each other in the literature, right? Because they won't say you're full of whatever, right? But they will say, I think your fossils are actually dubiofossils. Next slide. All right, so here's the main points from all that, okay? I can imagine a lot of things that life does that I could set up an instrument to go and look for the stuff that life does, right? Whether it's making a certain gas, whether it's some microbial, some shape feature that looks like a microbe. There's a lot of stuff that life does that I could build an instrument and say, find that thing that looks like life. And the hard part is eliminating what we call abiotic processes, things that are not life, but that do things that mimic life. And the hard thing, like if you want to get into the philosophy of like what our real challenge is as scientists looking for life beyond Earth, is there's a balance here, because this issue would make you say, well, let's just be really strict in what we're looking for. But if we're too limited and too strict, we'll also miss some weird stuff, right? Like one of the questions I get is like, you're talking about aliens. Like, shouldn't you be expecting something weird and not just like what we have on Earth? So that would cause us to like expand our horizons or our expectations and our measurements a little bit. But on the other hand, we also want to make sure that when we actually call the president and have a press conference about like whether or not we found life or not beyond Earth, that we're right, okay? We don't want to be fake news, okay? All right. So now that's kind of like a history of our field, like, and a lot of it's contentious, right? And that's part of the scientific process too, right? Scientists will put out something really big in the headlines, like we found life on Mars or ancient life on Earth, like the oldest evidence of life on Earth. And other scientists will say, okay, I hear you, but that sounds pretty like bold to claim that. Let me look in like excruciating detail about what you actually published in your paper, and I'm going to think of a way to reinterpret your data because of this rationale. And that is something we as a community now are carrying forward to our future searches for life. We're being actually thoughtful in advance about these ways that non-biological processes could mimic the signals we're planning to build instruments to go and look for. And then we're thinking, well, how can we use those instruments to separate out the like true living planets and environments versus the ones that are like, I call them like zombie planets, right? They're dead, but they look alive, right? So I want to be able to separate those things out. Okay, so did Mars ever have life? Now I'm going to sort of do a tour of the places we're going to look for life beyond Earth. And when we're looking for life on Mars, we're talking about like it's kind of like the Allen Hills meteorite. We're looking at the minerals on Mars. We're looking at fossil structures maybe. We're looking for the geochemistry, like the chemicals that are in that environment. Eventually, next slide, we're not just going to do this in situ. So that's the Curiosity rover. That's an awesome vehicle. The next step in this is actually not just sending a rover to Mars, but sending a little bit of Mars back to us, right? So we got that Allen Hills meteorite. And one of the issues with meteorites is we never get them purely fresh, right? They're crashing through the Earth's atmosphere, they're landing in Antarctica, and then humans are getting their grubby little hands on them and like contaminating them potentially. So it's better if we could actually send the samples back, which is what that last slide was showing. Like we'll get a rover, it's going to take a sample like a geologist would and like kind of bag it up like a geologist would, and then a second lander is going to come down with a rocket. The rover's going to send the sample to the rocket, and the rocket's going to actually launch the sample back to Earth. And that has a lot of advantages. The sample's fresh, but the other advantage is we have every single analytical tool on Earth and all the expertise of scientists across Earth to then apply to that fresh sample. Okay, so that's why we're going to send samples back from Mars. And when we're asking the question of is there life on Mars or was there life on Mars especially, we're also asking a more philosophical question, because this search for life in different locations will tell us other things other than just whether or not we're alone. On Mars, the second question we'd be answering is how does a biosphere end? Because we think that there's no life, at least globally, at the surface of Mars today, but it's possible that there was lots of liquid water on the surface of Mars billions of years ago. And if it had water at the surface and it had life at the surface in that time frame and it lost it, then the story of life on Mars is a story of how we lose a biosphere in the first place. Another place we're looking for evidence of life is on Europa and other icy worlds in the outer solar system like Enceladus. The way we're doing it in this case is actually we've got a few steps in the process. The first thing we're going to do probably in the next decade is, and by the way, the Mars stuff, the rover's there now. We're sending another rover there in 2020 to collect and store the samples, and then later on in the 2020s is when we'd send that sample back home, or maybe the early 2030s. For Europa, we're going to start with the Clipper in the 2020s. What this is going to do is it's like going to, for my generation, like Top Gun, right? Like you had like them doing the flybys, the tower, to like scare the pants off of the air traffic controllers, right? So we're going to be buzzing by Europa with the Clipper in the same way. It's going to actually not be in orbit around Europa, but actually around Jupiter. And what it's going to do is it's in its orbit around Jupiter, it's going to pass, here we go, really close to Europa every once in a while. And when it gets close to Europa, it's got a whole bunch of instruments on board. First of all, mapping out this sort of terrain on Europa and seeing where all those cracks are, but it's also going to have a radar that's going to find out how deep that ice is. And the reason we want to find out how deep the ice is eventually we want to land on Europa just like we've landed on Mars. And you want to land at a place where the ice is not quite so deep and you can get down to because we think underneath that ice shell, there's a huge liquid water ocean that's global in nature. We want to get down to that water because water, at least on Earth, is fundamental to life. By the way, that's why, it's almost a joke within our community. There's like a press release like every 6 months, like, hey, we found water on Mars. Again. And it's become a bit of a joke because water is like, for us, it's oil, right? Like, if you strike water anywhere, you strike a location that could harbor life. Everywhere we go on Earth, as long as there's enough liquid water in an environment, you find life. You could go to the driest place on Earth. If you find a little moist crevice in that like super dry desert, or if it rains once in every 10 years, you all of a sudden get blooms of life. Sometimes even huge plant blooms that are beautiful in the middle of a desert, because that's the one fundamental and consistent thing across our biosphere is where there's water, there's life. That's why we get super excited about it. So for Europa, we want to know how deep that ice shell is with the clipper, so we can send a lander that's as close to the water as possible and hopefully get some water spewing up to the surface, if not drilling down to it to go look for life there. Now for Europa, we're asking a different philosophical question, right? When we think of life, you know, and this is sort of getting outside the box of what we're expecting when we think of life and trying to not just constrain ourselves to the kinds of life we have here on Earth today. On Europa, there's a lot of water, but there's no sunlight at the interacting with that water because there's this ice shell that's globally covering it, right? So this would be like not just you, like as an individual organism, but like the whole biosphere being shut off from sunlight forever. Okay, that's whether or not that works. Like there's a lot of theory we've written up that says it could and it should, but whether or not it does is totally unanswered. And this is where, you know, the science comes in, right? We've got a theory that if there's water and there's nutrients and there's energy, and there should be some chemical energy under Europa's ice shell, then that should be enough for life. That's a hypothesis we're going to test with experiments, these clippers and these landers. All right, now this is getting to the really weird stuff. Does Titan have life today? All right, next slide, Mike. So this is so cool. This is, okay, most of the stuff I've talked about before is in some phase of like development or planning or funding. The mission I'm about to talk about to Titan is up for consideration for a mission slot. It hasn't been like formally selected yet, but it's one of 2 finalists to be selected for an upcoming mission opportunity. It's called the Dragonfly, and you can kind of see why. This is actually a drone that we are going to send to Titan to fly around Titan's surface, right? So it's going to be able to like land, and this is why it's called a Dragonfly. It's going to be able to land on these like methane lakes that are on Titan. So Titan has a hydrological cycle with like precipitation and evaporation and rivers and streams and lakes, but it's not made of water. It's made basically of like natural gas. It's like methane, right? It's wild. This Dragonfly could land on that stuff, like get a little bit of a test tube and like suck a little bit of it up and do all kinds of chemical analyses. This actually has a lot of the same instruments we're sending to Mars. If you've ever watched like CSI, it says like a whole CSI lab like packaged into the size of like a Mini Cooper, okay? And that's the same thing that we send to Mars. And although instead of wheels, it's going to have these 2 little skis and what's called a dual-layer quadcopter arrangement, so it can not just land in one place, but actually land in multiple places in these lakes, on the sand dunes, maybe some other locales. And this is like I don't know if anyone in here is like a sports fan, but for me, it's like I like watching things like the home run derby because you see like athletes like totally in awe of each other. This is that for me, right? Like I have nothing to do with this mission, but when like my colleagues pitch it, I was like, oh my god, it's like so cool. Yeah, this thing is awesome, but it's not funded yet. Like we'll see. Fingers crossed. And the big thing here is like there's 2 things that go on when NASA's thinking about what mission to fly. It's like how cool and exciting is the science, and how difficult is it for you to pull off the like Dragonfly drone you're sending to Titan. And those are the 2 things that this team's going to have to worry about the next couple of years and prove to NASA in this ongoing competition that it's the one that we're going to send somewhere else. Next slide. So with Titan, we're asking a different question in terms of the search for life. Now, I should say that the Dragonfly mission isn't being designed from the ground up to search for life, but it is making measurements that could, in theory, detect life if it were there. Now, if we're looking for life on Titan, we're asking a different philosophical question. We're asking, like, is weird life a thing? Every time I give a public talk about this, every time I give a science talk, if it's to a non-astrobiology audience, if I'm talking to my mother-in-law about what I do, like I get the same question over and over again, which is like, are you thinking outside the box? Are you thinking about like not water-based life, non-carbon-based life? Any life on Titan is not going to be water-based because water is locked up as like in mountains, basically. There's like ice mountains on Titan, another like crazy thing. So the life there would actually be existing in these methane, ethane, natural gas-like lakes. And in that solvent, you actually probably would not want to be carbon-based. You'd probably want some other biochemistry, at least not the same biochemistry we have on Earth. So like for Titan, the question we're asking philosophically is this weird life a thing? Okay, so now the last place we're going to look, and there's other places we could look, you know, Enceladus, Venus, but for the most part, the plans we have on the table are the ones I just mentioned, with one more, and this is the place that I probably have the most familiarity and expertise, and this is the missions that I've been working on the most. So the last question is, do exoplanets have life? And this story for me starts in our solar system because our expectations start here with our 9 planets. I know, like we're supposed to say 8 now, but to me, Pluto's still a planet, all right? So, like, and that's not just me being like an old curmudgeon that learned that in grade school. Like, I think the best version of this is someone says like, this thing passes the Captain Kirk test, right? Like if Captain Kirk were looking at this thing, he wouldn't say like, I'm looking at a dwarf object. He'd say there's a planet here, right? And beyond that, like the differences in like morphology and the different kinds of features here, like this thing is geologically active. It's not just some like dumb ball of rock hurtling through space. So at any rate, that's my little rant. So 9 planets. There's a whole lot of diversity here, like in terms of the environments that they have. But one thing that we thought before we started looking for planets beyond the solar system is you had small rocky things, Mercury, Venus, Earth, and Mars, close into the star, and we had Jupiter, Saturn, Uranus, Neptune, and Pluto further out. Let's set Pluto aside for a second. These are all gas giants. These are all small rocky things. This wasn't separating peas and carrots in our mind. This was like separating like peas and grapefruits, okay? Like the peas were close in and the grapefruits were far away. That was sort of our model for how planets formed in all solar systems, because every model we wrote was basically designed to give us the solar system. Okay, so here's what we have now, right? Even if you think we lost Pluto, that's all right, because we've got thousands of planets we've found in the last 20 years. These are all planets around other stars. They're not this close to each other. They're packed this close to each other so we can show them all. So every single dot here is a planet we've found beyond our solar system that's orbiting another sun, another star. The size of the dot is basically scaling how big the planet is. How fast it's moving is how fast its orbit is compared to like 1 year on Earth. And the color is basically how hot the planet would be based on how close it is to the host star. There's a tremendous diversity here. So there's 2 things that have come out of this. The first is like, and I've told this story before, I literally look at the night sky differently now because of these discoveries. If you ask scientists 20 years ago, like how many planets are out there, they'd be like, I don't know. There should be like something out there, but like, you don't know. Now, we have an estimate. There is at least 1 planet for every star in the sky. So if you go out tonight and you count stars, you can even do this in the bright lights of Atlanta. If you count stars, you're counting planets too, right? There should be at least 1 planet for every star you see. And some of those bright stars, some of those stars might actually be galaxies, which actually would have billions of planets in them. The other thing that's changed is if I, 20 years ago, tried to say not just how many planets were out there, but how many planets that could potentially be like Earth, that were of the right size and the right distance from their star to have global oceans like we do at the surface, that could have global surface biospheres like we do. If I put out any number, doesn't matter what that number was, scientists would tell me I was like crazy and I shouldn't be saying stuff like that. But I can say it now, and I'm not crazy, okay? So if you go out and you count stars, for every 10 stars you count, not only are you counting at least 10 planets, but you've probably counted at least 1 planet that's of the right size and the right energy, so the right distance from the host star to harbor global biospheres, similar to the one we have on Earth today. That's an amazing statement, and we couldn't make it 10 years ago. Okay, next slide. Now the other thing that's happened, in addition to sort of those counting statistics, is we've just been like surprised over and over again. I was talking about like separating out like peas and grapefruits. Like what exoplanet science has done is it's like put the peas and the grapefruits and made it into like some disgusting toddler smoothie thing. Because like nothing is separated anymore. The very first exoplanets we found were hot Jupiters. These are the planets bigger than Jupiter, the biggest thing we have in our solar system, but closer to the sun than Mercury, to its star than Mercury is to our sun. Right? This is the exact opposite of what our models were predicting, because our models were designed to recreate the solar system in which we live. The next surprise, or the next surprise I'll talk about at least, were these super Earths. So these are planets that are like bigger. They're not like Earth with superpowers. Okay, they're things that are like kind of Earth-ish, but like bigger in size, and they're smaller than Neptune. Now we don't have anything like that in our solar system. And so our models, which were designed to recreate the solar system, were predicting that these things would not exist. Turns out, they're the most common thing that we found in our local neighborhood, right? So again, the models were like not just wrong, they were like the opposite of, the opposite of our predictions was what reality gave us. And then lastly, there's planets like Kepler 16b. So, and by the way, every planet has like a boring catalog name like this, just that's how we like keep track of them. So Kepler 16b, this is a planet orbiting a double star system. So like, I like using the beer as an example because I can have some of this nice Ironmonger beer. So imagine you have two stars sort of orbiting each other at the center of a system, and you have a planet orbiting like way outside of it. That's called a binary star where the binary is interior. If you were standing on the surface of that planet, you would see a double sunset as that planet's rotating because both the stars would sort of set at the same time. Now that's awesome, but our models said that those were impossible. And so nobody thought that these things could exist, except maybe they were looking at the wrong source literature, okay? Now, when Star Wars came out, the astrophysicist said, well, that's poetic, George Lucas, but like that's impossible. Turns out he might not have been right about whether or not Han shot first, but he was right about this, okay? He was right about this. All right, so how are we going to look for life on these things? Because all we know so far is like their astrophysical properties. We know how big these planets are. We know how far they are from their host star. We can make some estimates to say like, where oceans are and are not possible, but we aren't looking for life yet. That's about to change. So this is a telescope that's being built at the institution I work at, the Goddard Space Flight Center. This is the James Webb Space Telescope. It's been in the news this week because it's delayed. We can get into that in the Q&A if you want. It's awesome. Like this thing is plated in gold. It's 6.5 meters across. Hubble's about this big across, right about my wingspan, maybe a little bit bigger. Webb is like the width of this stage across, so like 6.5 meters. So it's kind of hard to show, but like a telescope, the size of this stage compared to something that's a little bit taller than me, that's a tremendous amount of collecting area. You can get a lot more photons with this. What that means to scientists is we can actually start to not just see these planets, but take the data, the light we're getting from the planet, and split it up into little tiny color buckets. Now that's important because color is how astronomers and astrophysicists and earth scientists look for chemical composition, because certain gases in the atmosphere absorb certain wavelengths of light. So if we see a dip or a peak in sort of the color distribution coming from a planet, that'll tell us if it has water, it'll tell us if it has carbon dioxide, and in some cases, it might tell us if the planet has oxygen or ozone, the gases that on Earth are made exclusively by algae and plants, okay, the gas we're all breathing right now. So James Webb is not designed to do this, but because it's such an awesome thing, it's going to be able to do this for some stars. There are some planets that we're about to discover with the test satellite that's going to launch later this year. These are planets around M-type stars. So next slide. JWST is going to be able to probe their chemical composition of the planets and look for signs of life on them. The problem is, I'm not optimistic we're going to find anything there. And the reason is this awesome cartoon. So this is actually Mars. This is data from Mars that's being recreated with this awesome visualization. This is from measurements made by the MAVEN spacecraft. What the MAVEN spacecraft is doing is it's exploring basically how an atmosphere can be sort of blown away from a planet, right? And if you don't have an atmosphere there, there's a bunch of problems. First of all, you can't breathe, kind of an issue. Secondly, if you don't have an atmosphere, you can't hold liquid water in at the surface. It goes straight into steam and you lose it immediately. There's no liquid water phase. And this is, now at the end, this is that high resolution simulation now mapped to the MAVEN data. And this is, the high resolution simulation comes from a model. In this case, our models are actually matching the measurements really, really, really well. What MAVEN's teaching us is that you can actually lose an atmosphere fairly easily if you've got a lot of high energy radiation from the host star. The problem with the JWST, the James Webb Space Telescope's exploration of life on planets around other stars, it's going to try, but the planet-star combinations it's going to be looking at are especially prone to atmospheric loss. Okay, so if all the details of what I just said, like kind of like it was just too much, like basically Webb's going to be able to look for life on planets that are like warm enough, like they've got enough energy from the host star in total to keep ocean stable, but it's getting too much of the high energy radiation that might blow atmospheres away and the planets might be dead. Like as a modeler, what I'm expecting is that Webb's going to see like a bunch of bare rocks without atmospheres and without life. Like that's just my expectation. But that's why we do the measurement, right? Because you shouldn't just like trust me. If I knew with 100% confidence that what I just said was true, there wouldn't be a point to doing the measurement. But that's what science is about. I'm making a prediction. We're going to test it with observation when Webb launches. So Webb will look for life, but in places that I'm skeptical life could exist. Next slide. Now, if you want to look for life in places that are more like our Earth-Sun combination, and by the way, the problem with Webb is the host stars it's looking at are like rambunctious teenagers that are like kicking things all around the room, and that's just too high energy. So if you want to look for planets around more sun-like stars and probe their chemical composition and look for biosignatures on those worlds, you need a bigger telescope. And that's something called LUVOIR. This is also something like the Dragonfly mission that's in the concept phase. It's something we're studying and basically pitching to the science community to see if this is what they want to be their priority going forward. I'll tell you, I'm biased. I'm the deputy study scientist on this mission. I love it, and I plan to spend the rest of my life working on it if it gets selected going forward. So I'm biased towards this one, and it's like near and dear to my heart. Next slide. But if we built it, we'd be able to look not just for signs of life, but we'd be able to look for signs of life on planets that are pretty much like the Earth around stars that are pretty much like the sun. And not only would we be able to do that once or twice, we think we could do that for about 30 to 60 planets, depending on which version of LUVOIR we're talking about. So at that point, we're starting to ask different questions. The philosophical question here isn't just, are we alone, or is there life on like LUVOIR 5c, or whatever the planet's going to be called? We're asking, do global biospheres exist beyond Earth? We're also going to be able to ask other questions, like why is there life on these planets and not on those planets? And when we do that, just as I said, like, our models were all wrong about the solar system, well, guess what? When our models were wrong, we didn't just like give up. We went back and changed our models, and they're better now. And not only can they recreate all the surprises that we found when we looked for those exoplanets and found things that didn't fit our models, our models reproduce that stuff now. They also now tell a better, more accurate story of our own solar system. 20 years ago, before all those exoplanets were found, we couldn't really predict why. We didn't understand why Mars has the size it does in the orbit it does. And we do now. And the reason our models can predict Mars today and it couldn't before is because our models got better by being wrong and fixing them to fix the mistakes that they had in them, okay? What I want, the future I can't wait to see 30 years from now, are when our models are a little bit off from the LUVOIR data about how a biosphere interacts with its host planet. When those are wrong and we improve those models, we'll have a better understanding how life and a planet interact. And that's going to be better for all of us, whether or not you care about the search for life. Okay, so, Earth is really important to me for a number of reasons, not just because I depend on it to live. It's also academically where I got my start. I was a physics major in undergrad, but I went to grad school in geology. And the reason I did was because if you want to understand life as a planetary phenomenon, you have to think about life in a planetary context. And so everything I do, everything I take to the job of looking for life, whether it's on Mars or Europa or these exoplanets, it comes from a framework of thinking about how complicated Earth is, about how many different systems we have interacting on Earth, right? And NASA has acknowledged this complexity. This is an awesome video of all the things that we've got out there observing our host planet. And now as you zoom out, you actually see things that are observing the sun, because part of what drives our environment is energy coming from our host star. We look constantly from above down on Earth at its cryosphere, how the ice sheets are changing. We're looking at the atmosphere and the carbon dioxide in the atmosphere. We're looking at the biosphere and where life is and how that changes over the seasons. We're looking at land use changes. We're doing all kinds of detailed investigations of our host planet, and we're tying that back to our host star, which is giving us the energy for life and for a lot of our civilization. When we do that, that doesn't happen in a vacuum, because there's astrobiologists like me that are leveraging all that, because when we do that, we're developing new theories, new models, new science all the time based on the data that's coming back on Earth. And then there's scientists like me saying I want those awesome models, so I can apply them to the search for life on planets around other stars or even to other planets in our solar system. I literally wouldn't know how to approach the problem to begin with if it weren't for the foundation that's been laid for me by all these amazing Earth scientists over the last 30 to 40 years. To give an example of this, I talked about the search for life as being like an assessment of chemistry. If you want to know how we could see life from space, or across interstellar space, the best way for me to describe this literally is to show you a map of how we can map life on Earth today. These are satellite observations that NASA has made with the CWIFS mission and the CWIFS instrument, which is tracking life on the surface. You can see forests grow and shrink in the northern hemisphere, alternating with the southern hemisphere seasonally. You can also see blooms of chlorophyll, of algae, growing in the ocean periodically. So in other words, we can detect life remotely. You don't have to be there scooping up sand to know that life is there, because we can see the specific colors associated with chlorophyll in the oceans or with forests on land. And not just the stuff that life has in it, not just the chlorophyll and the leaf structures, we can also see the gases that life produces. In this case, this is a beautiful map of data from the OCO mission, which is looking at the carbon dioxide in our atmosphere, another NASA mission. And you can see gases in our atmosphere remotely. What we plan to do for these exoplanets is take these same techniques that look for CO2 or O2 or methane, or in the case of the prior slide, the chlorophyll in the forests, and we're going to apply it to a telescope looking at a planet around another star. And that's how we're going to look for life. But it leverages all the stuff we've learned from doing it here at home. Now, when we're looking at Earth, the fundamental question we're asking, because it's not a mystery whether or not there's life on Earth. We know if there's life on Earth. But we're trying to figure out what its limits are. We're trying to figure out how far can we push life into the most extreme environments before there's not life anymore. And we also want to know, how does life interact with its host planet? What does life do that impacts the host planet? And what does the host planet do that impacts life? And how does that relationship play out over the billions of years of Earth history that we have access to here at home? Next slide. Oh, that's it. All right, so I guess what I'd like to do now is just say thank you for your attention. I'm going to stay up here and take questions from the audience. Read the catch box? All right. All right. All right, so this awesome thing is called a catch box. It's a microphone you can throw, right? It's like a microphone in an Earth box. So raise your hand and we'll try to toss you the mic for a question. All right. Start off with the easy one.
Hello, thank
Yes,
you for
hello.
the presentation.
Thank you.
I just wanted to ask a question.
Yeah.
About landing on Europa. Many people have brought a concern that when we detect, because searching for life, would actually detecting life would be brought with the probe. It's very difficult to clean the probe to destroy all the signs of life from Earth.
Right. So the question, because there's a little feedback, is when we look for life on Europa, some people are worried that we're going to basically bring life with us and just detect ourselves. That's a huge problem. There's actually, I think actually the coolest title in the federal government is Planetary Protection Officer for the United States of America, right? And literally their motto, the motto of that office is all of the planets, all of the time, right? It's the one office I feel should come with a super cape and tights. The job of that office is actually to worry about that exact problem, to make sure that when we send spacecraft to a place we're going to look for life, that we don't contaminate it with the life we have on Earth. And that's both for moral reasons, because we don't want to contaminate other planets with our life here, because we should decide whether or not that's a good thing to do as a society, not just some scientists messing up in the lab. But it's also important scientifically for the reasons the questioner just put out there. We want to make sure that we're not bringing life with us. So we've got a whole range of measurements and standards that we utilize to make sure we're not going to do just that. Now, the other aspect to that office is if we bring samples back from Europa or from Mars like we're planning to do, they're also making sure that the science fiction horror movie version of bringing samples back doesn't end up happening, and that we're all safe from contamination from those other planets as well. Yeah.
So you had mentioned, I think it was Titan, that you had the Dragonfly mission that you were looking at with the drone. For a drone to work, it has to have a pretty substantial atmosphere. And so I was sort of surprised that it had that much of an atmosphere that a drone could actually fly.
Yeah, so Titan is special in that way. It actually has, it's one of the few planets that has this hydrological cycle, but also has a pretty dense atmosphere in it. And the molecules that the Titan's atmosphere are made of are actually more massive than Earth. And so the mean molecular weight of the atmosphere is higher. And that gives you it's actually good for all kinds of aerial stuff. People have also pitched balloons and airplanes. Basically anything airborne works pretty well on Titan. The drones is something we're looking at right now because the technology for drones has advanced so rapidly the last decade or so that we think that that's relatively mature in terms of doing airborne stuff on another planet. I should say that people are also talking about putting a helicopter on Mars as part of the next Mars rover payload. For Mars, what you just mentioned, like the lack of an atmosphere because the atmosphere is thinner on Mars, that becomes a pretty big problem. But on Titan, it actually works out pretty well.
How do they know that a meteorite came from Mars?
Oh, that's a good question. So the way we get at the source of where a meteorite came from is actually looking at its chemistry. Both the gases that are contained in it, and if you know what isotopes are, it's basically like the same molecule or atom, but like a different mass for that atom. Both the isotopic composition of the meteorite and the gas composition match Mars's atmosphere really well. And there's some gases that kind of stay constant over time, and we're using those as sort of the tracer. We didn't like see it launch off Mars because that happened a long, long time ago. But it's basically matching the composition of the meteorite to that of Mars. It could have come from somewhere else, except most of the places it could come from, we've also mapped out those compositions, and they also don't match. And like, I mean, I'm kind of glossing over a lot of detail here, but like when I say composition, it's not something that would vary between like here and Maryland, where I flew in from like the other day and where I'm flying home tomorrow. Like, it's something that's kind of constant over the whole planet's environments. Yep.
So as an undergrad student, you were studying physics, and as a grad student, you were a geologist. How do you turn that into astrobiology?
All right, so a couple things. One, I sought out specific places that were good at astrobiology research. So where are you at? Like, you're a student in what level? High school junior. Okay. So a few things. I don't recommend anyone follow like the exact path I followed, like unless that's like the thing that you think is like super awesome. To be good at astrobiology, you have to be good at a few things. You don't have to know everything. Like that's the trap. Like some people say like, oh, like astrobiology is like astronomy and biology and geology and physics and chemistry like all like mixed together. So I'm gonna like take a little bit of all those things. I actually think that's a bit of a trap. Like Admiral Akbar would tell you it's a trap. Instead what you want to do is you want to get really good at that like one discipline that like you can be an expert in, eventually get a graduate degree and be like the world's expert in one tiny corner of knowledge, but have those things be related to astrobiology. Like you can be an astrobiologist, there's no one I know that's just an astrobiologist. Like I'm literally one of the oldest people alive that has a degree in astrobiology, but I have a degree in astrobiology and geosciences. Okay. Other people have degrees in astrobiology and chemistry, or astrobiology and astronomy, or astrobiology and whatever. You have to have a home discipline you're good at, and you're bringing that expertise to the question of are we alone? And if you want, like, I'm not going to, especially because I'm online, I'm not going to give you advice on specific institutions like on a live stream, but if you come up afterwards, I'll tell you some really cool places to go to college that are doing amazing things. Okay.
Back here again.
Yep.
I just had a curious question about the private and public sector. Are you guys going to eventually have to? Are you partnering with like the current private sector that's up and coming?
All right. So this is an interesting question because like the first thing I think that we need that like people like me up on stage need to do is actually clarify something in public-private partnerships. A lot of NASA actually already is a public-private partnership, right? Like if we build a rover to send to Mars, or if we build a telescope to send to space, like a tremendous amount of the work that we do is actually done by private aerospace companies, right? And we're partnering with them all the time. Like when I go to astronomy meetings now, probably about a quarter of my meetings are with companies, not with other astronomers, because those companies have the engineering expertise and know-how to do a lot of stuff that we really need to make these things work. So there's sort of this deep history of public-private partnerships that we have had at NASA to just make all this stuff possible. Now that all said, like if I just ended there, it'd be a bit of a dodge, right? Because like there is talk about actually doing like private space flight being a new player. Now like I'm sure people have seen SpaceX in the news, right? And like one question I get a lot is like, oh man, you work at NASA, like are you worried about SpaceX, right? The part of NASA I work in, which is like the science wing, like when SpaceX launches a new rocket, we're like cheering, like literally, like I was at my computer, like cheering with everybody else, and it was from two things. One, I mean, it was cool, like it was awesome. But two, if SpaceX builds a new, really capable, less expensive rocket, that's great for me because I can put a rover or a telescope in that thing and launch it up to space. Now, the third aspect to this is like there are people talking about doing like basically private space flight science missions, like a privately funded, like a GoFundMe campaign for a telescope or a rover or something like that. That hasn't happened yet, but people are seriously talking about it. Like, and if it happened, I would be happy that it was happening because I'm a scientist and I love the data. I think the most important thing there is that when that stuff starts to become, I don't want to say reality, but when it starts to get funded to the point where they're actually going to do it, we need to have conversations between the public and private space to make sure we're not competing with each other, but we're looking at different targets or different investigations on the same target.
Hey, Shawn?
Yeah.
Shawn, right here. Right up here, buddy. Right here. It's Kennda. I know you can't see me.
Yeah.
Here, I'm going to come up front.
Yeah.
So I was actually going to say, from the Mars perspective, I can already kind of talk about this for you.
Yes.
So Shawn's an expert exoplanets. My planet of focus is actually Mars, and I sit on a committee called the Mars Program, Mars Exploration Program Analysis Group, and this is an analysis group that is part of the entire Mars committee. And what we do is we kind of assess the state of the Mars exploration program, not only NASA but internationally. And we all talk to each other about upcoming missions, what are the major science questions and things like that. So in the last couple of meetings, it's called MEPAG for short. Well, in the last virtual meeting we actually had representatives from SpaceX talking about their most recent launch to Mars and what their plans are for human exploration. So the conversation, at least for Mars exploration, has already started where we have invited SpaceX and private industries to come in and communicate with the science community as part of the community with regard to what are our plans for Mars exploration and the next steps as we kind of move towards planetary exploration and having this private partnership, because they're planning to send a human mission to Mars, and we want to be talking to each other because we're planning to send a human mission to Mars. So that's already kind of happening, at least for Mars. But it would be great if we could see it happening across the entire program, just like Shawn said. But I just wanted to give you that update because I'm pretty sure you don't do MEPAG meetings.
I don't do MEPAG meetings. Thank you.
Oh, wait, actually, I'm going to give it back to this lovely lady. Gave me back the microphone.
By the way, one of the challenges in science is work-life balance, which Gavin's giving us a great demonstration of right here on the stage.
Okay.
Where are we at?
I'm going to pop this back so she can ask her question. Thank you for giving me back the microphone.
And in addition to writing our congressman to give you guys more funding, is there anything else that the private sector, you and I, can do to help you get things funded?
I think like share your enthusiasm in general for the stuff we're doing. Which, I mean, this is why I'm like really happy to be here tonight, right? Like I am legally prohibited from lobbying Congress, and I can't even tell you to lobby Congress, right? Like that's something like according to the Hatch Act, like I can't do. But what I can do is I can share my love for like the science and the cool stuff that we've got on like in the pipeline to maybe do in the future, and do everything I can to promote the next generation of scientists coming up behind me. And that's the other thing I think everyone can do, right? Like if you've got students or you've got kids or you've got friends or neighbors that are thinking about doing this stuff, like encourage them, because there's actually a huge future here if we reach out and grab it. And the stuff I'm talking about, it's not happening tomorrow. It's happening 5, 10, 20, 30 years from now, which means if you're an undergrad student, if you're a high school student, like you could write your PhD thesis on the data from the LUVAR telescope I'm trying to make happen, right? Like, and you could be at your stage of your career that I'm at in my career right now, right? Like that, it's not happening tomorrow. So the other thing is just support young people that are trying to get involved, like Gavin.
I've got the mic now. I'm originally from Flagstaff, Arizona. Visited Lowell Observatory where they discovered
nice.
Pluto.
Awesome, yeah.
So thank you for acknowledging
lots
Pluto
of planets found in that neighborhood.
as a planet.
Yeah.
My question is, discovering and releasing information about our own planet. How involved is NASA in, I mean, we've got so many oceans that are unexplored, the deep history of our planet that we still have yet to discover.
Yeah.
How involved is NASA in that aspect?
Well, so NASA is involved in a number of ways. There's the thing that NASA is most involved in is Earth observations, which I was talking about a little bit today. Like if you see like a weather weather radar satellite, like that was probably launched by a NASA-NOAA partnership. So we're involved in almost all of the stuff that's looking back down at Earth. But it actually goes further than that. We work with NOAA a lot, partially to get to Antarctica and do exploration of environments down there and the Atacama Desert. We do a lot of work on Earth today looking at extreme environments that are cold or dry or really deep or really dark to see the limits of life. Now, the other thing that NASA is doing is it's funding Earth history research, right? Because as someone said at this great Georgia Tech Astrobiology conference that I was at yesterday, we actually have 4 different versions of Earth spread out in time through its geological record, not necessarily spread out like 4 Earths we found around other stars. Like, if I went in a time machine, like a DeLorean or like a TARDIS or like a hot tub or something, and I went back 3 billion years, I'd be in a heap of trouble unless I also brought a gas mask, because there would have been no oxygen there. But there was life present at the time. So like, and actually this, I'm kind of geeking out a little bit because this is like what my dissertation research was on. But like, there was like 1 billion years at least where there was life on Earth, but no oxygen for animals like us to breathe. And oxygen's the main biosignature we'd be looking for on exoplanets. So NASA's has been investing in decades, including like my PhD research, into those questions so we can better understand not just how to find modern day Earth life, but like ancient like Earth life. So there is a thing there. NSF is also a big player in that space, and we collaborate with them a lot.
Okay, you're talking about Europa, how it has you speculate that it has liquid water underneath the ice surface.
Yeah.
Why would that water not be frozen? Is there some sort of internal heat source?
Yes, you got it. So there's a few internal heat sources for Europa. One is just like the remnant stuff, like imagine like all the stuff when the planets form smashing together, everything gets really hot and then cools down. It actually takes a long time for it to cool down, especially because there's radioactive materials inside the center of planets that are still generating heat. But that's not the real reason Europa still has an ice shell. The real reason is it's getting like slung around Jupiter all the time, and when it's getting slung around, it's gravitationally interacting with other moons as they pass by each other. And when they gravitationally interact, there's tidal forcings, the same way that like the moon around our Earth is like causing the oceans to slosh around and like we have high tide and low tide. Same thing's happening on Europa with the ice shell. But there's no water to slosh around. And because there's no water to slosh around, all that tidal energy is going into the ice shell, and it's kind of like flexing it back and forth like this. And that flexing, just the like mechanical motion of that is generating heat. Like, I don't know if you've ever done like any like woodworking or anything like that at home, but if like you're sawing something or drilling something and it gets hot from that friction, that's what's happening on Europa, and it's generating just enough heat to keep some of the ice melted 1 kilometer to 100 kilometers deep. Good? Where we got it? Oh, down here. Yeah.
So I've heard that the next telescope might be able to examine the atmospheres of exoplanets, which might give an indication if there was life. Do you know how they could tell whether or not an exoplanet has life or probably has life?
So the observations you're talking about were from that like awesome gold telescope I was showing earlier, the James Webb Space Telescope. And what's going to happen there is planets are going to pass in front of the star. We're only going to look at stars where we know there's going to be a planet passing in front of the star. When the planet passes in front of the star, the atmosphere of the planet is going to sort of serve as like a color filter. Like if you were up here on stage with me, you'd see some blue lights to the side. Or if you ever work on it as a stagehand, you'll have like red and blue gels. Or like if you ever remember like an old school overhead projector at a school where like you put the sheet down and the light passed through it and it put colors up on the screen. The same way this works is there's a little thing in here that's actually generating specific colors that fly up onto the screen. All of those things work because you're filtering out certain colors of light. And the same thing's going to happen with these planets. They're going to pass in front of the star, and it's going to filter out certain colors of light. In this case, the filter is going to be based on what gases are in that planet's atmosphere. If there's a lot of carbon dioxide, it's going to block the wavelengths of light that carbon dioxide absorbs at. There's oxygen in that atmosphere. There's certain wavelengths of light, a little bit redder than the reddest things we can see. You'll see a little bit of a dip in the spectrum from that. And that's how James Webb's going to look for life. Now, I'm honestly not counting on it working because it's going to be looking at these planets around these like wild teenage stars that like are like way too active and wild and are going to cause all kinds of havoc for the planetary atmosphere. But we're going to look.
Got one right here.
Where's here?
To your left.
All right. Finally, we got over here.
Yeah.
Oh, yeah. Sorry.
No worries.
Gotcha.
So Earth has a electromagnetic core that provides protection for the atmosphere, and it would seem that that might be something that we could look for elsewhere to repeat a faulty model of relying on what's happened here.
Yes.
So are there sensing capabilities to detect electromagnetic subsurface activity to gather whether or not there's an atmosphere or other means of doing that? And then jumping ahead, do our electromagnetic signatures as intelligent life become apparent with the same sensing apparatus?
Okay, let me break that into, let me do the two. So let me do the first one. So I might have to ask you a question about the second one, so I make sure I understand it right. For the first one, yes, kind of. We haven't, to be honest, we haven't thought about it a lot. One of the challenges with all this stuff is we have to make sure that we're including as many brains as possible into the conversation. Historically, the people that do space physics and like space weather and like geomagnetic studies, like they haven't been involved in the study of habitability and biosignatures and stuff like that. And so we're aware of that science, and we've thought about it at a very top level to the extent that someone that's not an expert in it, so I'm not an expert in that stuff, but I've thought about it a lot. What we really need to do is engage that community more and bring them into the fold. NASA actually has, so there's 4 science divisions at NASA to get like geeky about like our organizational structure. We got Earth Sciences, which I was talking about, and Astrophysics. We got Planetary Sciences, and we've got Heliophysics, which is the science you were talking about. Historically, heliophysics has been the one that's had the least amount of interaction, but like there's stuff we've got going on with grants and new research programs that are trying to change that. And if you like are particularly active in that, like that might be a funding source for you in the future, or if you have friends that are. The second question about like could aliens detect us basically? Are you talking about like detecting like radio communications and stuff like that? So in theory, yes. Like we know how to search for signs of intelligent life, which by the way, I wasn't talking about SETI at all. And it's not that I hate SETI. It's just like that's not the kind of astrobiology that like NASA does and funds. Like, and part of it is that's not what you'd build a spaceflight mission to do, right? You would do SETI, you would search for those radio wave stuff with ground-based observatories. And I'm really glad that folks with ground-based observatories are doing that stuff, and I think it's cool and worthwhile. There's some interesting stuff about that. One thing that I didn't appreciate until I started talking to some folks is we're actually getting quieter over time. And part of the reason, like, so who now has digital television in some form, right? Or like television that they get over the internet or digital antenna. Digital transmissions are much more energy efficient than than what they're replacing. And as a result, we're actually leaking less of a signal than we were 10 years ago, right? So digital TVs brought us like awesome sporting events in high definition. They're also making us harder to see from far away. In general, you might expect that trend to continue in theory, right? Like because as our technology improves, just stuff should get more efficient overall. And then you'd look for other things, right? So then you have to think about what other things is our civilization doing that could be detectable remotely. And there's like that's a whole nother talk. So,
question for you. I know you were talking about Europa being opaque to sunlight, but what about, in addition to drilling through the surface, the use of remotely operated submarines to look for geothermal vents on Europa?
Yeah, so that's a great question, and I said briefly that like Europa has energy, but I didn't say where it came from. So I was talking about Europa having this ice shell that kind of isolates the water from sunlight. And that's not to say that Europa is totally devoid of energy, as the previous question was getting at. There's sort of these tidal energies. But the other thing that's happening is at the very, very bottom of that ocean, we think there's this geothermal activity, much like exists at the bottom of our ocean. And that's not only important for thinking about the water existing, it's probably even more important from thinking about the energy that life could use to make a living on Europa. All life needs energy. We get our energy by eating food or drinking beer that has organic carbon in it and burning it with oxygen. On Europa, what you'd probably do if you're a microbe is you'd actually use a set of chemical reactions, taking the oxidized space environment and comparing it to the reduced environment, chemically reduced environment of the interior, and basically taking a chemical disequilibrium, almost like a battery, and using that energy to build cells and maintain cellular structure. And that's If that isn't happening on Europa, which we think it is, it would be a major problem. But because that geothermal activity is there, we think that life could potentially exist.
Hi. You had mentioned in your presentation that they had discovered some life on Antarctica and it was discounted. What was the reasoning that they said that it was, just thrown out?
A number of reasons. Number one, if I say I found evidence of life on another planet, that's a super hot, it's so bold. The standard that I have to live up to by my scientific peers is tremendously high. It's about as high as anything else. Number two, there were 3 other experiments on that rover that did not find signs of life. That were also designed to look for it, right? So I think there were a total of 4 experiments. 3 of them were negative and said there was no life here, and that was the one that did. And then lastly, there was a complete absence of organic carbon, like the stuff that life is made of, also assessed at that time. Now, as a result, the astrobiology community over time has not been convinced by that. I think, this is what I would say. As an independent scientist, I don't really have a stake in this game, I'm not convinced by the data right now, okay? If we did more detailed experiments in the future that showed that life is present on the Martian surface today, I think it would only be fair if Gil Levin, the person that did that experiment, got credit for being the first one to find it, even if he didn't convince the science community at the time. There's actually a dispute over who found the first exoplanet, because the first exoplanet discovered wasn't believed until the second exoplanet was discovered. And then they believed the first exoplanet, but it's actually the second discovery that gets a lot of the credit, right? So if we ever convince ourselves that there is life on Mars, I think Gil Levin and his team should get the credit for being the first ones to discover it. But at this level, because of those other negative results and because of the lack of organic carbon on the surface, that's why most people doubt the claim.
Shawn, I think it's Kennda again. I'm right up
There you
here.
go.
I know you can't
Yep.
see me. I think the other question was also. You were asking,
Kennda would be great at this.
I was going to say, well, especially since I used to work for David McKay.
Yeah, that's right. That's right.
So I heard your question because I was like, So because I used to work in that group. Because you were asking about the Mars meteor, right? Okay. So here's the story. So
sorry, I was talking about the Viking lander, not the Mars
everything
meteorite.
you said is totally 100%.
But it wasn't the
valid.
Mars
I'm with you.
meteorite.
It was the meteorite,
Yeah.
and I can spin on this because I work with the team, so I know. So what happened is that they found, like Shawn showed you, they found these structures that they're like, oh, these are absolutely biological. Only biological forms can make these. So what they found are these things called magnetite crystals. And we have this thing on Earth called magnetotactic bacteria. These bacteria that swim in the ocean, and they make these crystals. They literally make minerals inside their bodies that line up and allow them to detect Earth's magnetic field, and so that they can swim along and move along Earth's magnetic field lines. So they found these crystals inside an actual kind of this actual kind of carbon structure that we found in the meteorite. We actually found these kind of weird carbon structures in the meteorite. And they are fairly unique to magnetotactic bacteria. So that's kind of the thing that made them say, oh, this had to be made by life. And it was deep enough in the meteorite that they were convinced that it wasn't contamination or anything like that. But the problem is that these magnetite crystals, another team showed, can be made in a purely chemical process. So the big argument that cast huge doubt on the Mars meteorite discovery is, well, were the magnetite crystals made by biology, or are they made by chemistry? And to make it clear, the process that this really brilliant chemist at Johnson Space Center came up with to figure out how to make these things by chemistry came up with, it's a really complex process, but it's a process that could have happened on Mars. So it is a process that could have made these magnetite crystals. So that's why we're just not convinced. It's not enough data to tell us that these magnetite crystals were definitely made by biology inside this Mars meteorite. So that's why nobody's convinced.
And that chemical process, we didn't know how to do it before we found the Allen Hills meteorite.
This is brilliant geochemist named D Goldman that he spent like a year figuring out how to do this chemically. But he did it.
And this story has motivated a lot of research in the field since then, because now because what happened there is like that team found signatures that we knew of no non-biological process to make those things.
Exactly.
And then a bunch of other smart people said, well, maybe I can make those things
It was
without
like a red
biology.
team, blue team, where they're like, well, we think it's this. You guys go and figure out if you can do it chemically. And they're like, yep, we did it chemically. Your stuff's not conclusive.
So the hard thing is, and this is what astrobiologists are trying to do now,
Yes.
we're trying to game out here's what we think our data are going to be for a future mission that would find life. And we're actually spinning up those sorts of like red team, blue teams now to find other ways to make those signals before we launch the mission, before we build the spacecraft, so that mission or that spacecraft could also have the stuff that would differentiate between the like chemistry, the pure chemistry versus the biology.
Exactly.
That's one of the things we're doing differently now than we did before the Allen Hills meteorite, is we're thinking about that stuff in advance.
Right. And we have a lot. Yeah, we have a lot of people doing this in the lab every day. So.
Yep.
All right. I'm going to give it back to this young lady.
Oh.
No. I got to give it back to this young lady who again let me have the catch box. There you go, sweetheart. Ask your question.
How do we know that all life has to be made up of carbon?
Oh, nice. That's that. So I'll be honest. We don't know that it has to be made up of carbon, and actually, there's chemists much better than myself that have like come up with ways to make life out of things other than carbon. Now, I'm going to give you two answers to this question. Okay, I'm going to give you the answer I would have given 5 years ago, and then the answer I'll give that I give today. Okay, 5 years ago, I would have said, yeah, organic carbon, like not organic carbon-based life, could happen. But as a scientist, I need a test to figure out what life that wasn't based on carbon would do. I have to understand not carbon-based life well enough to make a prediction of what it would produce that I could go look for. And I'm not a good enough chemist to do that, but maybe there's a good enough chemist out there. Okay, that was my 5 years ago answer. My answer today is there's some awesome chemists out there, and they figured out how to look for the signs of life that isn't based on carbon might make. And actually, one of them came through Georgia for a time. Sarah Walker, who used to be a postdoc here at Georgia Tech, she's now a faculty member at Arizona State. She's working with Lee Cronin, who's across the pond in England, I think, and some other scientists. And what they're coming out with now is like, instead of looking for the specific things that a particular organism that might be organic carbon-based makes, right? Like, so organic carbon-based organisms on our planet, the thing we look for a lot is like oxygen, or like we're breathing out carbon dioxide. We're looking for specific things that come from that specific biochemistry that's ultimately carbon-based. What Sarah Walker and her colleagues are saying is like, throw that out the window. What you really want to look at is sort of the complexity, just basically like a mathematical analysis of the overall complexity of the chemistry, the chemical network that is created by life. Because whether or not it's carbon-based or silicon-based or something else based, if life is in the environment, it's going to be enriching and developing the complexity of the chemistry around it way more than non-biological processes can do it. And it's like orders of magnitude, like hundreds of thousands of times more complex because of life. And that becomes our biosignature. Now that biosignature, the complexity of chemistry that life creates, it doesn't have to be because it's organic carbon-based life or silicon-based life or water-based life or anything-based life. As long as you agree with the fundamental principle that life is making the chemistry in its environment more complicated, which does seem to be ubiquitous, even for models of not organic-based chemistry, now you've got a biosignature that works. Does that work? All right. Oh yeah, you had a question over here. So back here, and then we got a question over here if we could do that one next.
When you talk to other scientists in other countries, how forthcoming are they with their research and data, or is it like more competitive?
Whew. Ask me after, and I'll give you I'll tell you a story that I don't want to tell on stage.
Okay.
In general, people are awesome, right? Like, and I actually believe as a scientist, it pays to be really generous with your data, with your models, because like, so I'm a modeler. Like most of what I do, I didn't really go into this today. Like most of what I do is I build models of planetary atmospheres to figure out what their chemistry is like, what their climate's like, what biology would do that would impact like the chemical network of an atmosphere, stuff like that. Everything I do, like, and there's some there's an instinct to be like really proprietary with my model and keep it like locked in and close to me, so only I have access to it and can write papers with it. But actually, I think the opposite instinct is a much healthier one. Because when I let my model out there to the community, two things happen. One, other scientists that have not developed a model like mine, they don't want to just like steal it and use it for their own purposes. They'll email me and they'll want to collaborate, and maybe they'll write a grant that gets me or my students some funding, and that's awesome. Also, like I might talk to them because they found a bug in my model that I really should fix before I write my next paper, and that's also awesome. So I think most scientists, especially younger scientists, like that are my age, like around 40 or younger, really buy into that model. That said, when you do, you are exposing yourself a little bit. Like I'm really open, like with my like crazy like fun ideas for like my next research grant. And I, at one point in a very stressful and tenuous part of my career, had research that I was working with with a colleague that went and basically published that research without me on the paper. And that was like I'm normally really calm and I can sleep well. Like I know I'm like really excited when I'm on stage, but like I usually don't stress out too much about stuff. Like I was losing sleep over it. It was horrible. It was awful. But I got through it because eventually I got my paper out, they got their paper out, and we resolved some of the science disputes in the literature, right? And in the end, like I can say 5 years later, like looking back on it, not in the moment, like it ended up being really healthy because we figured out some cool science from the differences in our results that happened when we kind of split. I'm kind of like venting a little bit now, but like the moral of the story is like if you are a scientist, be open with your data, be open with your methods. Someone might steal it someday, but that's on them and not on you. And you should just like go high. So, but overall, people are awesome, and I actually haven't noticed a huge difference in like their country of origin in terms of whether or not they steal data.
Who am I taking it to? Okay.
Hi, thank you. Well, thinking about, you're talking about modeling.
Yeah.
I'm interested when you were talking about the peas and the grapefruits.
Yeah.
And that everybody expected Class M planets to be small and close to their suns. But now you know that we're the weird ones. So
yeah, the solar system is
what does it
Portland.
makes us so weird? Why are we?
Why are we Portland?
Yes.
Yeah. So the thing that we're probably missing the most are those super Earths. That's the thing that seems to be super common that we don't have. And this goes back to like the fixing the models thing. So to make those hot Jupiters, by the way, it's easy for us as scientists to like misrepresent this. Those hot Jupiters were the first things we found, but it wasn't because those hot Jupiters are really, really common. It's just that those are the planets that gave off the biggest signals. So when we were first developing these instruments, they weren't like super sensitive, and the biggest signals were the first things we saw. So the hot Jupiters, there was like an observational bias, right? Like the only thing we could see were the hot Jupiters, and like, oh my God, we saw hot Jupiters, right? Like, who would have guessed? Finding the hot Jupiters, finding the super Earths has caused us to rewrite the models on how planets interact with each other gravitationally, and how they interact with like gas and dust in a planetary system. And what we now know, to explain a hot Jupiter, what we now know is that planets can migrate over time. You can form a gas giant out here where we think gas giants could form, and then as it interacts with gas and dust in the disk, it can actually move over time closer to the host star, which is how we think these hot Jupiters exist. They didn't form close to the star, they formed out where Jupiter formed and then moved in. But because we put the physics of that into our models, we now know that this probably happened in our own solar system. And it actually explains a whole bunch of stuff we couldn't explain before. For one, we think the planet Jupiter and Saturn probably moved in a little bit at one point in solar system history, and they moved back out again. And that had two massive consequences. One is it kind of cleared out a lot of debris around the region of the solar system where Mars exists, and it kind of like sucked all that mass out, so that is why Mars ended up being as small as it is. At least that's the way the models are explaining it now. The second thing is when those planets moved, oh gosh, I'm trying to think of like a good analogy. Like, it was kind of like the system was full of dust and like these small rocks scattered all over the solar system. And as soon as those gas giants started to move, they started to gravitationally like move some of that dust and the small rocks around. But as soon as they started moving around, they started moving the other things around. It was almost like a set of dominoes, or like taking like a house of cards and knocking one card down, and everything just collapsed. In this case, the collapse was like all these small rocks all over the solar system, as soon as Jupiter and Saturn moved, basically getting slung all around the solar system and crashing into planets. And that's one of the reasons we think that the moon has the craters it does, is from that motion of Saturn and Jupiter. And actually the dating of those craters is really well explained if you had a one-time event like that. This is one of the places that looking at these surprises we've seen in these other planets, like the hot Jupiters, has helped us understand why the solar system has its properties today. I don't know if we have a good explanation as to why we don't have super Earths, which is the weirdest, most Portland-like thing about our solar system. Someone does, but it's not me. So, Where's the mic? No.
So can you comment on how this latest research is affecting the result of the Drake equation?
Oh, yeah, I love that. So who knows what the Drake equation is? All right, so maybe like a fifth of people. So the Drake equation is an equation that, that was written like 40 years ago. And the purpose of it was actually to organize a conference about this very topic I'm talking about tonight, which is like, is there life beyond Earth, and how many, in this case, like Drake was like involved in studying the search for intelligent life on other planets. He wanted to just get a ballpark estimate for how much intelligent life is there in the universe or in our galaxy. And the way he broke that up, because that's like a hard question to answer, is he broke it up into like basically a number of factors that get multiplied together. So he said it's like, depending on how you write the equation, you could say like it's the number of stars in our galaxy or in the universe, or the rate at which those stars form, times the fraction of stars that have planets, times the fraction of those planets that could have conditions that are ripe for life, times the fraction of those planets that could have life that actually do have life, times the fraction that have intelligent life, times the lifetime of a civilization. Okay? What's interesting is since Drake wrote down that equation, we've actually been marching down that set of terms. Actually, I should walk the other way from your perspective, right? So like when Drake wrote the equation, we had a pretty good handle on how many stars were out there, but we didn't really have any information on anything else. Now first of all, we have a better, tighter constraint on how many stars are out there, but more importantly, we now know how many planets are around those stars on average, and we even have a handle, although there's a bit of error bar around them, about how many planets are around those stars, or what fraction of those planets have conditions that could allow for life. And the next step in the Drake equation is to figure out, of that subset of planets that could have global biospheres like Earth, how many actually do have life? And that's what the LUVOIR telescope is. It's actually being designed, you could think of it as being designed to measure the next term in the Drake equation. And the next mission after that would actually go back to like looking for intelligent life and signals of intelligence or civilization on those worlds. So from like the scientific method, and I don't think this was intentional, because we don't like sit around and like plan our stuff around the Drake equation, but it's just so happened that like each term is more difficult than the one before it, right? Right. Up here? Here, I'll play shortstop.
Hello. So, if there were life on Europa, you know, maybe it might be really cold.
Yeah.
Eutectic slush of water and ammonia and methanol or something like that.
Although I'm from Chicago, so cold is relative.
So am I.
All right.
Lane Tech High School.
Nice, Glenbrook North.
So, if life existed at really cold temperatures, would it do anything? You know, like,
yeah.
Could you have a fish that could swim? Would it have enough energy, or would it just like maybe divide over the course of 1,000 years and be such low energy that you wouldn't be able to detect any metabolic byproducts or anything like that?
So that's an excellent question. I don't know the map of the energetics of Europa compared to the volume of ocean to give you a solid answer. I will tell you my intuition is that you're probably onto something there. However, the people that are actually experts on this stuff, like that come from the background of like looking at Europa, and by the way, all of you folks in the Atlanta area, I hope you recognize it. Like, first of all, there is some amazing astrobiology going on at Georgia Tech and at Emory. Like, I was at this conference yesterday with local researchers. And on Europa in particular, like one of the best scientists in the world on Europa is Brittany Schmidt, who's a faculty member down at Georgia Tech. If you ever see Brittany Schmidt at one of these things, you should ask her that question, because whatever she says, you should trust over what I'm saying right now. What you're saying concerns me with regards to Europa in terms of the amount of energy that is input into the system, the temperature of the system, and whether or not life would be slow to reproduce in that context, in that environmental context. But let's assume that our theory really has that as an expectation. I still think the right thing to do is to develop a test of that hypothesis, right? You still, I think, go into Europa and say, like, you would make a prediction of like what the standing biomass size would be per mole of water, per liter of water in the European Ocean, and then make a measurement and do a cell count and see if your prediction of the biomass size matches what's actually in there. It's a concern. The Europeans that know more about me aren't too concerned. All right, we got a couple questions back here.
Trillion planets in the galaxy. How come ET hasn't contacted us?
The Fermi paradox. Okay, so why, if there's all these planets out there, why haven't we been contacted by ancient civilizations or by alien civilizations? So for astrobiologists, the question of why, and actually if you look historically at the question of if all these potential abodes for life exist beyond our solar system, as Carl Sagan put it, look up in the stars, if there's nothing out there, it'd be a horrible waste of space, right? And why haven't we been contacted yet if the universe is teeming with all this life? What I think is interesting is if you look back at the history of the scientific responses to those that specific question, it's a bit of a Rorschach test, right? If you ask Carl Sagan that, he would have said, because he was living at a time when the biggest threat to our civilization was nuclear winter, right? He was worried about he was living in the Cold War. He was worried that we'd really damage our environment for decades, if not centuries, with the clouds that would exist in the wake of a nuclear war, in which there is no winner. So his answer was, civilizations blow themselves up, because that's what he was worried about as a scientist. If you look at the literature today on that very question of why haven't we been contacted, the most kind of popular answer today, like the flavor of the month for the answer right now is well, if you assume exponential growth, because that's part of this, right? You assume if you move to another planet in 2,000 years, then after that each of those move to two more planets, and then to 4 more planets, and 8, you keep doubling the number of planets you're inhabiting. On the time scale of astronomy and geology, that, you fill up the whole galaxy. That equation presumes exponential growth. And every ecological system we've looked at, whether it's a microbe in a test tube, to something existing in a riverine or a land-based system, to our own society when it's been placed on islands, to concerns we have today about ourselves as a global species, every single scale you ever look at, exponential growth is inherently unstable over long time periods. And so the most popular answer today is exponential growth is unsustainable, and that's part of the assumptions to the Fermi paradox of what that assumes we should have been contacted by now. And what's interesting is the scientists that are talking about that, what are they actually worried about on the side? They're thinking about climate change, and then exponential growth in our energy usage as a society is problematic. So that seems like a good answer to me today, but maybe that's just because of some bias I've got in my head right now, just like Sagan 20 years ago had concerns about nuclear winter in his head. And I hope that 20 years from now we're over the climate change problem and we've figured out a way to address that, and some scientist in the future is giving you a different answer to that question.
Yeah, the last question is that on many occasions you mentioned carbon, but you have a tendency to put the word organic in front of carbon.
Oh, yeah.
Why do you put the word organic in front of carbon? Why don't you just say carbon?
Well, it's not because I'm a hippie that likes locally sourced produce at Whole Foods or Trader Joe's or something like that. Although do support your local farmers, that's a good thing to do in general. When I say organic carbon, yeah, thank you, because that's jargon and it's confusing jargon. That's not the kind of organic I'm talking about. When biologists talk about organic carbon, they're any element or many elements can have different states they exist in with regards to their environment. Organic carbon is the carbon that exists in the form that life uses it in. If you're a chemist, we say it's reduced carbon or it's fixed carbon, but it's the carbon that's not like it is in carbon dioxide, which is inorganic carbon that's not part of biological organisms. Organic carbon is the stuff that forms hydrocarbon chains that are the basic basis of the chemistry of at least all Earth-based life. And that when we say organic carbon, we're not talking about farmers market carbon. We're talking about the difference between the kind of carbon that's in biology versus the kind that's not. And biology can actually turn the inorganic carbon, like in the atmosphere, into organic carbon, but that takes energy. And actually, that is the demand that another one of our questioners was getting at. Like, if you actually have to expend energy to do that, you need an energy source, and it has to be big enough to make that happen. We do that, like the way we get our organic carbon is whether the bananas coming from Trader Joe's or like a big Mega Mart or whatever, we're getting it from some other organism that's already turned the inorganic CO2 into organic carbon. Some plant has done that for us already, and that's where we get our organic carbon from. Okay.
Okay. Thank you very much,
Thank you.
Shawn. Thank you. Thank you. We're just gonna give a minute for Dave to get up here.
Thanks, Dave.
Again, we want to thank you all for being here. I have another special guest for us. This is Dave Sheets. He is the owner of the brewery and the head.
I'll keep the commercial very quick. So anyway, just thank you guys so much for coming out. And Shawn, thank you. I mean, I just can't thank you enough for coming out.
Yeah.
And giving us some wisdom. So thank you very much.
Thanks for giving me some beer. It fuels the wisdom.
I hope that's a good trade.
Yeah,
actually.
awesome trade.
Really. So anyway, tap room's open till 11. We do lots of fun stuff in this room, like comedy nights and live music and all that kind of stuff. So if it's your first time here, go onto the website, sign up for the naughty list, come say hi. Okay, great. Thank you very much.
Thank you all.
Yeah,